Good afternoon everybody and welcome to today's webinar. My name's Peter Shields from EMF Scientific and I'm excited to be here at the Docklands in Melbourne visiting the Telstra 5G Smart Apartment today. I'm joined by Mike Wood and Steve Iskra from Telstra, and today they're going to run us through some of the work they've been doing in the Smart Apartment, including the work they've been doing with the new 5G mmWave down converter antenna from Narda.
Well, thanks Peter, it's great to be here. It's great to have you here at the 5G Smart Apartment. We're going to go upstairs in a minute and take you up and show you the awesome view. What we've got here, along with our graduates, this is a project with Telstra and Telstra's graduates. We've set up over 100 devices connected up over Wi-Fi and mmWave, all over 5G, and they're running in the apartment. So we're activating a number of high intensity use cases. We're also measuring all of the different Wi-Fi bands and the 5G bands, including the new mmWave. And it's great to have this new kit. I think we're the first operator globally to try it. And we're going to put that through its paces upstairs. So why don't we go upstairs, start the presentation, and then we'll come back after and take questions.
First of all, Mike, would you like to just give us a quick rundown on what's actually happening here today?
Sure. Well, thanks Peter, and thanks for the opportunity to come live to everybody today. As you said, it's Mike Wood. I'm here with Steve Iskra from Telstra. Very proud to be here. We're running live from the 5G Smart Apartment here at Docklands in Melbourne. We're going to show you a short presentation and the setup that we've got here, but we've actually got, this is a collaboration project with the Telstra graduates from 2021 and 2022. You'll probably see a fair bit of activity as we walk around and show the apartment at the background, but if I just step over here and turn the camera around slightly, we're actually very spoilt because the grads at the moment, they're about to live stream cooking pasta or cooking our 5G pasta. We're doing database searches on the main desk, and I think when the pasta's done, they'll be back to their workstations. So we've got some lovely 5G pasta to look forward to as we go forward. But what we might do is share the presentation. We're in Docklands in Melbourne in Australia. And the purpose of this is really a number of things that we're looking at. Firstly, the 5G performance. What's the customer experience like? We're looking at the mobile and fixed wireless access connections. We've got more than 100 devices actually. There's about 120 connected devices running in this apartment. Many of them are on 5G and many of them are connected over mmWave via Wi-Fi. We're looking at a variety of use cases, and really importantly, with all of these connected devices, what are the EME levels? Because people often ask us, look, is it safe to be on 5G? What if you've got lots of devices? And that's what we're going to demonstrate today. So where are we? We're in Docklands in Melbourne, down at New Quay. And for those that are familiar with Melbourne, we're at this building on the right-hand side. Specifically, we're in where that yellow dot is. We're highlighted in that yellow dot. So we've got a lovely view from Docklands in Melbourne, and there's a map there with a pin showing where we are. Now, at night time, it's a spectacular view, and you can see the harbour and the bridge lit up from our presentation point. So just a bit about Telstra's 5G, first of all. Our 5G network currently reaches 75% of the population. We're in more than 3,200 suburbs and over 200 cities and towns across Australia. And I guess our mission is to bring better connectivity to everyone, especially with 5G. And that's what we're doing in the capital cities, metro, and importantly, we're extending our reach to the regional and rural areas. Our history with mmWave actually dates back many years. Last year was our 5th year of 5G in Australia. We launched in 2019, but we've been experimenting and testing, particularly mmWave 5G, since 2016. Where we launched our first test bed in Australia. It was actually out in Clayton. We built our 5G Innovation Centre up at the Gold Coast, and that's been a hub of activity to allow us to innovate and really produce some fantastic results with 5G. Last year, we bid for some spectrum at the auction, and we had Australia's first mmWave handset launched. And of course, in 2022, we're coming to you live from the mmWave Smart Apartment. So to give you an idea of what we've done, on the left-hand side is a classic graphic showing what mmWave or what 5G antennas can do compared to the old 4G. So 4G you tend to send a signal equally in all directions. And with 5G, we've got advanced beam steering so that we only need to send a signal to the devices that are connected. Now, in the graphic, it shows you an ideal connection to some cars, to some people, and to an apartment building on the right-hand side. Well, that's exactly what we've done here at Docklands. You can see the condo apartments in the picture on the right-hand side. We've got a base station directly across the road, and we'll show you that live in a minute. But we've up-tilted the antenna for this use case, so we're servicing all of the apartments in that on the upper floors with our mmWave antenna. So in terms of the setup, you saw that picture before, beautiful apartment building down here. Like I said, we've got over 100 connected devices. I think most homes typically would have between 20 to 30 devices. Well, we've put over 100 in this one to really stretch it and test it. They range from a range of things like the Google Home products. We've got doorbells. I love the robot vacuum cleaner to clean up after us. We've even got a 5G smart coffee machine. I'm going to show you my favourite one later, but we've got a lot of EME monitors inside the apartment and outside, particularly measuring what the mmWave levels are like and what the mid-band is like. In terms of devices, as we walk in, we've got a range of different devices streaming 4K. That's just to give the apartment some initial load, in addition to everything that we put into it. The sort of speeds we get, anywhere from 2.5 gigabits per second up to 3,800. That's the sort of speed we're getting here in the apartment. We just ran a speed test before and we were at about 3,200 to 3,500. Now that's on mmWave over 800 megahertz, and we're going to show you that bandwidth and the EME testing shortly. Gaming has been very popular. Now I know with the teenagers, and we had a family stay here last weekend, and I honestly don't know if these boys got any sleep because they were gaming on mmWave on the couches. They set up desks and they set up benches. But if you look at the two photos here, they look like they're in the same position the next day with a beautiful view over Melbourne, although I think I like the nighttime view. But one of the boys, Charlie, he said to me when he set it up, "Mike, the ping is 0 to 1. That is awesome. You can't get any faster than that." And I think they had a great experience. Importantly, I said this was a collaboration project with our graduates. Now, the reason we're doing this is, look, they're our future. They're the leaders and the technology leaders of the future. So bringing them into the real world, letting them experiment, set up and try out devices and equipment, and importantly, learn about all the EME stuff is so important to us. So it's a collaboration and a learning exercise. And you know what? We have a lot of fun doing it. They're cooking 5G, it smells amazing. So I'm so looking forward to having some 5G pasta at the end of this live stream. And if mmWave works really well, we could probably share it virtually. I don't know quite how that's going to work, but maybe that's a use case we can try. Now, one of my favorites is coffee in the morning. And I think this was the picture you used, Peter, when we sent out the, this is like Melbourne every day. I had a great espresso out on the balcony. Now, we are testing lots of different equipment. You can see next to me there is the new Narda mmWave probes that connect up to the SRM 3006. So we're very fortunate that we've been able to get a loan of the probes for a couple of months. I don't think there's any mmWave in Germany, so they've got nowhere to test it. So fortunately, we've got a great network and we're trialling at all of our venues around the city, but importantly in the smart apartment. And on the left-hand side, Michelle was convinced, we just unpacked the smart coffee machine and she was giving me instructions on how to drive it over the app. But talking about testing, I'm going to introduce Steve Iskra. He's going to talk through the various aspects of the test we've done. So Steve, if I move out of the way and hand over to you.
Yeah, so as well as having a good time here and cooking lots of pasta and having the grads in to do a bit of experimentation, a key part of the work here is to look at mmWave and the way it actually gets into the apartment and to look at the levels. So from an exposure point of view, an EME point of view, an EMF point of view, we're very interested to see how mmWave is picked up both outside and inside an apartment. And we had some very interesting results that we share with you here today. So as Mike said, we've got the Narda instrumentation, but we also had other instrumentation that allowed us to do these measurements. And we were kind of also guided by standards like IEC 62232, which I'll mention coming up. So we did some testing of millimetre wave signals only. And what you can see here, maybe just on the outside there on the balcony, you see a what we call a CASA antenna on the left-hand side, which is basically a fixed access point, millimetre access point. And down the right-hand side in that yellow kind of highlighted area is a millimetre wave base station antenna. And what we've been looking at is driving some signals from a millimetre wave base station antenna towards the apartment and measuring the signals. And we've done that by using a speed test application where we measure on the downlink and we activate the base station signals. So you can see we have one measurement that we performed on the balcony, and then we perform many measurements inside the apartment. So let's go to the next one. So the measurement approach basically was to use the speed test app to exercise downlink from the base station towards the apartment. We thought we'd use the IEC 62232 spatial averaging approach, 3-point spatial averaging approach there, doing measurements at 1.1, 1.5 and 1.7 metres above the floor. But and we're using a horn antenna. So this is kind of different to the sub-6 isotropic antennas where you basically take the probe and it'll give you a total field strength measurement, irrespective of the direction of the field coming towards the probe. Here we're using more directional horn antennas because that's really all that we have at the moment. And so what we had to do at each point, we had to rotate the horn into 4 different azimuthal directions. So we chose the first direction. We point the horn to the maximum signal that we could pick up. And that was typically basically towards the base station. And then we chose 3 other points in 90-degree steps. And we summed the levels that we found in watts per metre squared. And we also had to take a vertical and horizontal polarisation of fields. So we ended up with 12 readings, sum those readings to give a total incident power density for each point. And of the 3 points, we then did a computer spatial average value. So what you can see, the observations are probably not, they're probably in some ways not difficult to understand. So the highest level that we measured was on the balcony in clear air, free space, compared to the ones that were inside, which were lower levels. The other interesting thing is that when you point the antenna directly towards the base station, that level was at least 10 times higher than any other direction that we found. And that was really whether you're on the balcony or inside the apartment. The pointing directly towards the base station antenna gave you the highest level. There was some backscatter, we noticed, in a couple of measurements, but they didn't exceed the direction directly towards the base station antenna. And the highest spatial average value that we measured on the balcony is 4.23 by 10 to the minus 4 watts per metre squared, or 0.0042% of the general public whole body reference level. As I said, that was on the balcony. Another interesting observation that we made was the attenuation loss into the apartment. So we did a number of readings in somewhat different spots, but we found attenuation of the order of about 15 to 20 dB. So, and mainly due to the tinted glass. So there's a metal oxide coating on the glass to give the whole apartment some thermal efficiency, but that doesn't give you great efficiency for millimetre wave penetration. So you do get loss through the glass, which is kind of very interesting. So that's an observation. And here are the levels that we measured inside and outside on the balcony, 0.0042 versus the others, which are at least 10 dB down, you can see there. And bedrooms with window open, just point the antenna through the gap of the open window compared to the window closed. So certainly closing the window reduced the level that you measured significantly. Now let's move here. So maybe at this point, we might do a test to show you the attenuation through the glass.
So in this demonstration, we're going to show you how much the radio frequency signals, particularly at these millimetre wave frequencies, are attenuated when they travel through this heavily tinted and very thick glass window and door. We're going to run a speed test and we'll have a look at the spectrum analyzer and we'll see what happens when we open the door, and you should see the radio frequency signal on the screen increase. So I'm going to run a speed test. You'll start to see a little bit of activity, and I'm now going to open the door, and it's risen considerably. It's in fact gone up by 20 to 25 dB. So that's well over 100 times. That just shows you what happens when you've got these very high efficiency buildings with this window tinting. They really attenuate millimetre wave signals.
Live look outside the smart apartment at the moment, and if somebody wants to open the door, that way I can sort of show people what we're seeing. But okay, so before you could see the probes, and it's a little bit pixelated, I'll hold the phone still. This is a live view directly outside, and you can see the millimetre wave probe and also the mid-band probe. As I walk outside the apartment, I'll turn around to see if you can see the base station. Now I'll see if I can hold it still. Can we see the base station there, Steve? Is that showing in the
Yeah, mid-picture, basically.
Mid-picture. So the three black lines
that
are in the middle of the screen, that's the base station that we're connected to. And as I move the camera up slightly, this is the fixed wireless access antenna that's providing our millimetre wave connection to the apartment. Today we're demonstrating how we measure the EME, or electromagnetic energy levels, on millimetre wave, which is our new high band, high speed network. What we have here is one of the millimetre wave probes. It's connected to a meter inside. The one next to it is a probe that measures our mid-band network, or the other 5G networks. They're both connected to spectrum analyzers where we can read what the EME level is like at this point, and it's coming from the base station that we can see across the road. So Phil, if you want to come in, we'll do a measurement on the screen. And what we have here is a spectrum analyzer, and this is measuring our millimetre wave spectrum in the 26 gigahertz band, and this is 800 megahertz worth of spectrum. And if you have a look in the top right hand corner, it gives you an average level. Now that's reading 0.0007% of the public exposure limit, so very, very low. When I run a speed test, we'll start to see some activity on the millimetre wave band, and we'll see that figure increase. We're now starting to see the average level increase, and we'll wait till it stops, and then we'll take the reading. So the downlink is about to stop in a moment, and it's almost stopped, and we got 0.01% of the public safety limit. And now you'll see the average is dropping. Now that's running the network under a very high load, but 0.01% is 10,000 times below the public safety limit. What we're going to demonstrate now is we're going to demonstrate the measurement of EME levels running normal everyday applications like watching a movie or watching 3 movies at once. And we're going to measure the EME that was on the balcony from the probes we just showed you before. So if you want to come in, Phil, I'll show you the spectrum first. This is the millimetre wave spectrum. This is 800 megahertz of spectrum, and you can just see occasional green bursts of energy. Now that's the energy used to download the data for the movies that we're running. Now we're actually running 3 simultaneous movies, but the level that we have is 0.0014%. So that's a very, very low EME level. So what's generating that traffic? If we have a look over here, Phil, what we've got is some awesome quality on our 4K video here. This is streaming live over 4K, and this is Hawaii. It's the beautiful colors of Hawaii, and what a picture quality. That is live on millimetre wave streaming on 4K. Let's have a look over here on the iMac. Now this is Canada. This is another 4K video. Again, awesome quality, but look at that picture from Canada. Again, millimetre wave delivering spectacular quality. But we've got a third TV running, so if you're running 3 movies at once, generating that really low EME, here's another picture, or here's another 4K video. This is of a coral reef. So again, really awesome quality. Now, what we found before when we had a look at that spectrum analyzer, the levels were really, really low, and that's what's generating that these 3 movies together, or these 3 videos together, are what's generating that very low level. If we run a speed test,
which loads the network, we can also see if anything happens to the quality of the picture. So Phil, maybe have a look at Hawaii, and I'm going to run a speed test that will actually show, that will load the network, and we'll have a look at when it's running. The speed test is running now. Nothing's changed to the picture quality, and if you have a look over here, Phil, you'll be able to see that we're running the speed test on the network. Awesome speeds. We were getting about 3,600 megabits per second and just under about 100 in the uplink. So nothing was happening, but the EME level went up slightly to about 0.001. So it went up slightly from what we had before.
One is an electric field probe, and that's the one I've got in my hand. It has a little E symbol on it, and the other one is a horn antenna. So the horn that we had mounted on the balcony is pointing straight to the base station, and that's because that provides us with a constant signal. Now, what we've got here is this is the electric field probe that typically you'll use when you're quite close to a small cell or you're on a base station rooftop. Now, the difference between this and traditional probes, and you can see a probe in the background, is that this has a donut-shaped antenna pattern. So it sort of does this, but if you point it directly to a source, you're actually pointing it to a null, so it's actually reading a null reading. You have to orientate the probe up and rotate it to get the maximum level. Now that's quite different to how you might normally do EME readings, particularly with probes like this. Now we've actually been out to the street and we've done some demonstrations. We're too far away from the base station for this one to work indoors. That's why we have to use, a very expensive spectrum analyzer and horn antenna. But we've actually been out to the street, so we might show the testing we did. If I can give you this probe for a sec. Out of the view of Docklands, just down around the corner is the car park. So we've got a mmWave small cell for people that are coming into the ground so that they can connect up, as well as all of the people in the venue. There's a photograph of myself. It was a little bit cooler last Friday, so I actually had my coat on. But you can see the small cell in the background. So this is the testing example we want to show. Now, remember before I said that if you point the probe towards the source, you get a lower reading than if you hold it up. We're going to show you the video in a minute, but this is essentially, these are the readings we got. We were directly across the road, probably about 20 meters. We weren't that far. We were running a speed test at almost full capacity, and in the null position, we were reading 0.014%. So a very, very low EME reading. But when we rotated the probe up or tilted it up, we measured a signal that was about 5 times higher, 0.055. So that shows you the difference between pointing directly at the base station and holding it up. So one of our observations is that you're going to need to orientate the probe so it's not pointing directly at the source. And in consultation with Peter and with the Narda team, really it's a matter of moving the probe around. Now, we've actually got a short video that we'll show you, and then we'll show you these results.
Hi, it's Mike Wood from Telstra here, and we're very privileged to be able to be testing the new Narda probes, the SRM 3006. But we've got the 26 gig mmWave probes. We have a horn antenna and an E-field antenna. So this is the omnidirectional antenna, ideally used for when we're measuring small cells at mmWave, like you can see in the background. Now this antenna actually has to be orientated vertically to pick up the most signal because it has a donut-shaped pattern. Now, Phil, if you want to show what the pattern looks like, it has a minimum if you're pointing straight towards the small cell. So if I was pointing towards the small cell, I'm actually reading a null. I have to rotate the antenna up so that it's picking up the maximum level. And through our tests, what we've found is it's about a 5 to 10 time difference between pointing straight at the small cell and holding the antenna up. Now this is probably going to be ideal for when you're on site doing compliance boundary tests, or if indeed we're checking the background level of small cells like we're here today. So I'm holding the probe up, I'm moving it around to get a peak reading, and as we found before, when we compared it to the horn antenna, the results were very close.
So that was the explanation of how it works. and we'll now show you the screen readings that we got. Okay, so in this test, we're looking at a speed test, and we're going, and the average is 0.008. 0.00. Now, Steve, if you rotate it up, let's see if the average increase, and it is increasing quite significantly. So what that demonstrated was basically if you are pointing the probe directly towards the source, which many measurement officers typically would be doing, there's a different measurement technique. There's nothing wrong with that. It's just that you'll have to be familiar with how these probes are used. We've been using them on rooftops, and we've been using them on our street cells, and we've got early prototype versions. I think you know, they're coming to production probably about middle of the year. But, you know, it's great that we can get in there and we can help do the initial evaluation. So what have we found overall? So in the apartment with over 100 devices running, we've been measuring Wi-Fi throughout the apartment. We've been measuring all of the 5G, 4G and 3G bands, but we particularly focused on mmWave at the moment. We've got about 5 weeks of data to start processing. So we've got a lot of data that we intend to share with people over the coming weeks and months, but we thought we'd share with you at least what we found on mmWave to start with. So as you could see, the levels are very, very low. And when we opened the door and shut the door, you could see that attenuation. So inside, and I think as Steve mentioned before, we got a level on the balcony of 0.0042. Now that's over 10,000 times below the ICNIRP and the Australian safety standards, down to a level of, I can't even read how many zeros, 0.00002, almost at the bottom of the you know, noise floor. But really what we're finding with 5G, particularly mmWave, and you might have seen that if you could see the spectrum analyzer running before, because the data transfer is very efficient, the levels are much lower. We're transferring that data much lower than, you know, or we're transferring that data much quicker, and the EME levels are really low. Now, I know a lot of people have been asking about if I put a small cell, if I'm opposite a small cell, which we are, or if I've got a 5G antenna on my roof or outside my window, which we have, what are the EME levels like? Well, with all of the Wi-Fi, with all of the other services in here, we are definitely less than 1%. But as you saw, the mmWave levels are extremely low. Where to from here? Well, look, we are live in the smart apartment. Our testing is continuing. So we finish up in here soon, but we're going to be out in the field at a variety of sites doing the mmWave test, continuing what we shared with people last year. And this whole project is a continuation of what we started in 2020 with our first smart apartment. So we are going to continue to share the results. It's great that we can be here to share them with you today, or at least give you a feel for what we're doing. I'm going to stop sharing the presentation, and I must admit that pasta is smelling terrific. So the grads have really stepped up to the mark here. But look, Peter, I can't see the chat, so I don't know if we've got questions. I'm sure there are questions out there, but maybe if I can ask.
So, Amy, could you, is there any questions?
No, there's currently no questions at the moment. If anybody has any questions, please feel free to type them in the chat box and we'll address them as they come through.
Sure. Well, look, maybe I'll ask the first question then, Peter. Obviously, we've been comparing, you know, the Enritsu, the Keysight, some calibrated horns, and the new Narda gear. When do you expect that to be available here in Australia or in the market?
Well, we expect that these probes will be available sometime in the next 3 months. Excuse me, in the next 3 months they should be available.
And I mean, we've provided some observations, and you know, one of the things that we've been talking about, particularly with the E-field probe and the horn antenna, and if I grab this for a sec, the E-field probe, there's, you know, my initial observation was that there's going to have to be fairly clear instructions on how to use these, because so many measurement officers are used to orientating the probe towards a source. And I work in the world of standards. Now, I haven't quite worked out how you describe a swirling motion yet. So that's something that we're going to have to sort of look at. But as Steve mentioned before, we've been following the methods in the IEC and Australian test standards where we do some spatial averaging. And the procedures are quite detailed to get very accurate results. So I think there's going to have to be certainly some information provided on how to use them. And that's something that obviously we're providing feedback to Narda with. But
Yeah, I think your feedback to Narda has been very helpful for them understanding what they really need to do.
Just on that, I mean, you do have the other the straight horn antenna.
Yeah.
So that's also going to be available as well.
Available at the same time, yes. It should be.
So and I can see there's one question in the chat, or somebody's got their hand up. We'll come to you in just a moment. What we've found with mmWave, we're in an apartment facing the base station, as you might have seen from the photos and the bit of the live cross that we did. But the apartments directly behind us have no coverage. So you might find a situation where people say, hey, we really want you to measure in our place, but you go in there and you can't test anything. So it's going to be a real challenge to explain that, I think, to people.
And I think that therein is the issue of exercising the network.
Yep.
So a commonly available app is the speed test app.
Yep.
Which is a very useful app to allow you to kind of generate some activity from the base station, so you can actually check that there is something happening.
Yes.
So you know, that's something that'll be part of what people will do to actually make measurements.
And you know, thinking ahead to you know, the new IEC 62232 edition 3 standard that's coming out shortly, that steps through a number of methods. And I think you were showing one of those methods before with the spatial averaging, but being able to actually activate the network to a known level. It's all right when there's a lot of traffic on a network, but when the networks are quite new, you have to make sure that, of course, the networks are active and you know what they're doing to do relevant tests. Now, Amy, I think there's at least one
question. We've got Scott who's asked any details on the antenna mounted on the window behind.
Really good question, Scott. That is an antenna that's a, do you want to go and unclip it? And we'll bring it up and show you. Great question. We had an outdoor antenna that we showed you before. There's also a variety of applications where you can mount an indoor antenna that sticks to the window. And all you need is power, and it either connects over Wi-Fi or Ethernet. This one is being used in the US by Verizon. It's made by WNC. So it sticks on the window. The part that's facing out connects over mmWave to the base station, and the inside part provides 5G. Now, with this particular unit, you can get up to, so this is I think I'm showing it here. This is the part that faces into the apartment, and the back just clips onto a mounted pad on the window. We were getting anywhere from 400 to 800 megabits per second throughout the apartment with this device. It's very easy plug and play, but it has to connect through the glass. So you've got that attenuation that we saw before. So if there's a lot of attenuation, these work really well, but you might find an external antenna works even better, which it has been here. But no, these are great. So that's what this antenna is. It's a device that mounts on the window. It's basically plug and play. So we're evaluating these as to whether they're suitable for, you know, fixed wireless access installations like this. And it's certainly proving to be a very good device. I'll let you go to the next question.
Got another question here from Peter. Do you recommend that if there are concerns for EME exposure, that people get tinted windows? ? And does this mean that tinfoil hats are helpful?
Okay. Well,
Peter Ashmanal.
maybe the second part first. I honestly don't think a tinfoil hat's going to do a lot. You might get a few questions asked, but on the first question, this apartment is a 6-star rated energy efficient apartment. So it's got very thick glass, and it's got a metallic window film on it. At the lower frequencies, it doesn't really attenuate the signal that much. We've got 5G midband running in here, and our phones work really well on 5G midband inside. For mmWave, as you saw, with 20 dB of attenuation, that's over 100, 20 to 25 dB is over 100 times. So, if you want to block out mmWave, then that will work. But the challenge for us as network designers and network engineers is how do we provide good connectivity inside? And what we're finding is that the higher levels inside a place like this are typically Wi-Fi. So to answer your question on a purely scientific basis, the foil or the aluminium, what do you call it, the window film, and you can get attenuation ratings for this. It does block the signal at millimetre wave frequencies, yes.
And there's another question here is, what is the range of this probe?
The range of the probe. Okay, so what we're finding is that the horn antenna that's outside, and we're across the road, we're about nearly 200 metres from the base station, but remember we're inside this shielded room, or this, this room that's got high attenuation. These probes are struggling to measure the signal in here because of the attenuation. Outside, they're absolutely fine. So that's why we needed the very sensitive spectrum analyzer and a high gain horn. Where we typically use this is outside when we're on a base station rooftop, near a street cell or a small cell like in that video we showed, and out to a couple of 100 metres, these will be fine. So we're doing more evaluation on that to provide feedback, but really what you've got is, and I don't know if I explained this before, but in the handle, there is a frequency down converter. So it converts the 26 gigahertz or 20, I think it's 22 to 32. It converts that down to 4 gigahertz, but it's also got a preamplifier. So it's got batteries and you can also add a power charger to it, but there's a lot more electronics in this and the signal processing also that goes on inside the SRM. So the trade-off you get for doing that is it's not quite as sensitive as the original products, but they're not designed to do that. They're designed to be working on rooftops and working close to small cells. So that's how we will be using these. But inside an apartment building like this, where even our mobile phones are struggling on millimetre wave inside, one of these probes is probably not going to measure it inside.
I've got another question here. Did you observe any difference in the field levels averaged in the middle of the room and at the point close to the wall?
We did on millimetre wave. You did the averaging, I think, Steve, didn't you?
Yeah. So clearly, the closer you are to the window facing the base station is the best spot inside. As you move a little bit away, there is some drop off in signal. But I think one of the important things here is that line of sight becomes an important issue, whether you're inside or outside. As you move progressively inside the building and away from a kind of a line of sight view, it will drop off even further. So you are limited in terms of the way millimetre wave propagates inside an apartment. Effectively, inside any building, you're limited by propagation characteristics for millimetre wave, and so line of sight's an important issue. Very much so. And look, some glass, this glass here is quite effective at attenuating millimetre wave, but we've done measurements with plain glass in another apartment nearby, and that attenuation was only of the order of about 3 dB. So it really depends on the characteristics of the building and the building material as to what kind of attenuation you're going to be seeing.
And, I think the question was about scattering. We actually measured the signals in the apartment building across the road directly opposite, like you could see the antennas through the window, and it wasn't direct line of sight. We were measuring fields off the window frame, off the back wall. It wasn't a case of pointing at the source because the scattering was quite significant.
The further you go into the apartment and away from that view of the base station, you're going to see a drop off in the signal. So it's millimetre wave is quite a challenge compared to below 6 gigs.
And that's why, we're fortunate that we've got a range of instrumentation in our team here in Telstra, but, we had a situation where one of our RF assessors was asking us, look, how would you actually do this? Like I said, in the apartment next door, it's going to, none of our instruments will work in there. So it's really a case of if you can't see it, if it's not line of sight, then you won't be able to make a connection and you won't be able to measure it. So, we're going to be using this sort of kit with our other kit for all of our safety evaluations on our rooftops and our street cells. But when we're trying to measure the noise floor, you're going to need to, unless you can bolt on a super amplifier, Peter, you're going to need something else, because even our phones struggle to measure it. So, but maybe we can take the next question, Amy, if there's another one.
Sure, no worries. We've got another question here. Did you measure compliance distance from millimetre wave base station?
Yeah, really good question. We did, and we published those results last year. You might have seen, we could probably put a link in the stuff that we send out, but We published the 50 surveys of 5G millimetre wave last year, and the compliance distance, it really depends on the power you're running, and they're very low powered but high gain, and they're out to the order of a couple of metres. It's not that far in front of the millimetre wave antennas, and that's for a number of reasons. The efficiency is such that the signals are, you've got the spatial distribution of users. So imagine a whole lot of users here at Docklands. You're not sending a signal constantly all the time. You're sending multiple beams, so that brings the average down. And the utilisation, because we've got 800 megahertz of spectrum or 1,000 that we bid for, then we're able to utilise that energy a lot more efficiently as well. So the overall compliance boundary is quite small around these antennas.
Right, beautiful. We've got another question here. Can you clarify that you only have 1 millimetre wave device, so all smart apartment data traffic is aggregated to go through that?
Yeah, so we've got the one device out on the balcony that we showed you before, and all of the devices that we're running in here are aggregated. Essentially, that smart antenna, or the antenna outside, comes into an Ethernet box. It's split between our gaming stations, the iMac that we're running on, and our Wi-Fi routers, and the Wi-Fi is providing connectivity to all of the other devices, including, now you asked me this the other day, the other day, I love a coffee in the afternoon, but my favourite device when I love to make a cup of tea, now I hope Google's listening, but hey Google, boil the kettle. So hopefully Google is going to make me a cup of tea.
Okay, turning the smart kettle on.
There we are. It's going to boil the kettle, but I think I have to actually go and make the tea. But we've got robot vacuums, we've got all, hey Google, stop the kettle. We've got all of the devices through the different rooms that we have in this apartment,
turning off the smart kettle,
including the lights. But yeah, everything's connected over the device you saw on the balcony, and that's aggregating the level. That's why we're measuring the total level outside, and then we've done the characterization inside. So yeah, like I said, there's over 100 devices running in here, which is pretty insane for an apartment like this.
What were the maximum speeds you reckon we were getting on the millimetre wave system?
Look, it varies. So the Wi-Fi routers have a maximum of about 800 to 900 megabits per second. So over Wi-Fi, we're getting about 800. Connected directly to the iMac and the MacBook Pro, we're getting up to 3,800. And that's like, all these devices are commercial. We've bought them off the shelf and we've connected them up. I love working in the lab, but this is about taking the lab to the real world with our graduates, and they've been awesome in helping us do all of these connections. But that's the sort of speed we're getting, Steve. Was there another question?
No, that was the last question, guys.
Fantastic. So look, it's been a pleasure to share our journey. We've done a number of live streams, and this one we've tried to delve more into, how we're doing the measurements. And Steve's an avid follower of the development of the standards. We're really looking at how the spatial averaging works. We're trying a range of different instruments, including the new Narda kit. So thanks, Peter, for arranging that.
Thank you.
And when they get millimetre wave in Germany, I'm happy to come over there and show you how it all works, guys, along with our grads. But no, we're going to publish our results and share them with, as we always do, with our work. So look out for that. We'll post some of the clips on YouTube. We've got the demos. We've got high-res versions of the demos that we can give to you. But also a big shout out to, I know Sammy in Brisbane is watching. He's been helping us coordinate all of the graduates. We have 13 in the program. And I reckon the past is almost done. It is done, yeah. So it might be the right time for us to go and test the 5G Pastor Amy. And if you're close enough, we'll save you some. Well, thanks, Peter, for the opportunity to at least present today and to demonstrate the new Narda kit. It's certainly performing really well. We tried it in that small cell that we showed you in the video. It was a bit colder than Melbourne was today, of course. But no, it's been great to put this through its paces and how this is going to fit in with the mix of instruments that we use. And it was an awesome view up there. I mean, it was just awesome. I mean, it was
fantastic.
Yeah, and look, the questions we had were really, really good, I thought, in terms of the methods that we've gone to, how we use the horn antenna, the probes, how we've done some cross checks against this. When are these going to be available? I know we've got the pre-release version,
but when do they actually come to the
We're
market?
expecting them to be available sometime later this quarter, so before the end of the financial
Okay.
year.
Well, certainly put us down for on the list. In fact, you know, we've actually got them here, so I don't know whether you're going to get them back, Peter. But all right, look, thanks very much. I hope you've all got something out of this webinar, and we'll catch up with you next time.